thank you for joining Group Two's wonderful presentation entitled Predicting NBA Success. This is Team 2 from the Predict 498 Capstone Project Group, and our team's project was entirely based around the sport of basketball. So if we go ahead and go to the next slide. What we'll cover in our pretty lengthy deck here is we'll go over a quick team introduction. We'll discuss through our abstract, the problem and our proposed solutions. We'll discuss our research questions and our hypothesis. We'll do a pretty quick overview of the data that we had available, as well as the steps we took for data preparation and exploratory data analysis. We'll go through the models that we generated. And then finally, we'll get into ultimately an implementation plan for our project, show you an example of what our dashboard for the project implementation looks like. And then we'll talk through a few of the key project management components. Next slide. So to kick things off, there was two quotes that we found when we kind of were kicking this project around, and we chose these both because we completely disagree with both of them, right? So it says, you don't play basketball against opponents, you play against the game of basketball. You know, there's a certain truth to that, but ultimately you are playing against opponents, and opponents can be measured. The second quote there, the only important statistic is the final score. Ultimately, the goal of our entire project is to determine whether or not that's true. We think that there's a certain inherent value in some of the other predictive statistics, and ultimately we want to generate a model that can go through these and expose how these variables relate with one another and whether or not variables accrued through the sort of collegiate statistics can help predict NBA success. So next slide. Quick overview of the team. I'll let everyone introduce themselves. I'll start. I'm Ted Cragwell.
I'm Michael Chang. Hi.
I'm Jason Xu. Hi.
And Lakita, I think, was on mute. But anyway, so project objective, help NBA teams make better draft decisions. Ultimately, using NCAA statistics as a predictor, can we help teams make better draft decisions? Next slide. One of the reasons we chose to pursue this project is, despite the recent surge in metric calculations for sports, the NBA remains ultimately in the nascent stages of this sort of advanced metric utilization. The NBA, unlike Major League Baseball, doesn't have a dedicated feeder league. It hasn't had sort of the interest in sort of baseball's sabermetrics that it's had for roughly like 30 or 40 years. And predicting future success for NBA players remains elusive and largely untapped. So our goal is to use NCAA statistics to help further predict success and to create a model that's ultimately scalable and can help teams reevaluate their draft strategy when choosing players from college. Next slide. So how we're going to do that, the metric that we settled on as the largest indicator is the plus or minus variable. So it's one of the most widely used overall metrics. And what it shows is the ultimate impact, positive or negative, that the player had on their team's performance. So we wanted to find whether or not this metric was influenced by other predictor variables and whether or not we could successfully predict what a player's plus or minus variable would be given in their first year of the NBA, given their performance in the NCAA. Next slide. So how we'll get there, I will hand it over to Michael, who I think is going to go through the data we had and what we did with it.
Yep. So go ahead and go to the next slide. So I'm going to talk about how we got our data to feed our model, kind of the background and thinking we went to get there, and then all the cleaning and prep we had to go through it. So initially we had to make sure that we, again, are using NCAA data to predict NBA performance. We looked at a lot of different sources. Ultimately, what came up as the most comprehensive, both with holding college data and NBA data, was basketballreference.com. Some things we also had to consider as we were doing that was we didn't want to include players that did not have college data, and also wanted to make sure that we only wanted players that were drafted in and so in order to get that data, we built a web scraper, since it's not very easy to just download that data or compile it manually. So we built a Python script, which you can see a snippet here. And basically, we scrape the data off, the college data off of each individual player page. So if you go to, yep. So we had to basically go through each player for every single draft, identify if they went to college. If they did go to college, we would pull their college data. If they did not, we left them basically out of our script. So the script would go through every single player through all the drafts and take that data. In addition to the college data, it also had to go pick up the NBA data. And there's a lot of data on there, but specifically, we're interested in predicting box score plus minus. So we had to go and find that table and column and pull that out. Next. At the end of the day, we were able to get just over 1,000 players when we went back as far back as 1989. This was due to some of the columns that were being reported starting in 1989, as well as the amount of players being drafted. Prior to 1989, the drafts were much larger, but a lot more players didn't even make it to the NBA. So this is when they reduced the draft to 2 rounds, and we used the years going forward. We ended up with about 33 unique variables, mostly continuous, a few categorical, usually of all their college stats, as well as some background information. Next. We did have to clean out some of the data. Some interesting things we ran into were common names like Michael Smith, Sam Smith, some other ones. And so we had to create unique IDs. We'd also had to eliminate some of the sparse data columns. Some of the metrics that are relevant today only really started getting tracked in the last few years, such as offensive rebounds. And so we had to, after pooling all the data, we had to make decisions on what data we could actually use to predict for all our population. Thanks. In addition to cleaning the data, we also had to do some feature engineering. So the data we pulled was actually counts for the whole season, but given that certain players play different games, play different minutes, we normalized them per game. So we basically turned points scored over a season to points per game. Other things we did were normalize some categorical variables such as position. So in basketball, you have point guards, you have forwards, you have centers. So we had to do some normalizing there, as some players might play multiple positions. And then lastly, we also did a mapping of college and universities to divisions and conferences, because certain divisions and certain conferences are more competitive. And so by turning all the hundreds of schools into some division and conference hierarchy, we believe that will be much more predictive than just listing their school. Yes, and here's the slide for that. And this did end up helping our prediction value power a lot. So next, we'll be talking about EDA.
Okay, so once the data was gathered and transformed, we conduct the EDA, exploratory data analysis, with customer R code. And our analysis was based on the statistician 10 steps for data quality management. Okay, next slide, please. All right, so this is our code. Multiple box plots and other visuals were created for EDA, and we're going to show in the next couple of slides. Okay, so hold on, please go back. Yep. So this is the structure of the data. We have a total 1,012 observations for 45 variables. The variables can be divided into basically 3 categories, include players' information, for example, their names, positions, college, and the seasons they played in college. And another category for the data would be their total college stats and per game college stats. So that's how many games they played in college, and how many minutes, field goal percentage, and rebounds per game, steal per game, etc. Another category in this data set would be advanced player evaluation matrix. So that's BPM for the first 5 NBA seasons of these players, and then these variables are going to be used as a dependent variables for our models. Next slide, please. So these are the two plots. The title is kind of hidden here. So for the first one, I think is their draft, the age of the drafted. So you can see most players are drafted at the age of 21 or 22. I think it's going to be a lot younger today, since the league changed the rule of the draft, a couple seasons ago. And the second plot is the distribution of the games played in NCAA. So you can see most players played over 30 games in their college career, and less than 34 games. So that's about three seasons, I think. Next slide, please. This is the minutes they played in the NCAA, the distribution. Most players played around 1,000 minutes to 1,200 minutes in their college career. Next slide. And this is the correlation between the variables. So, for example, some of the variables are highly correlated with the season 1 BPM, which is our dependent variable, include total rebounds per game, steals per game, and minutes played. The more darker the blue is, means the highly correlated. The more correlated the variables are. Okay, next slide, please. Yep, so this is a box plot for minutes these players played in the NCAA by each position. So I think from this plot, we can see most players play similar minutes in their college career, regardless their positions. No matter their center, power forward, point guard, or small forward. So yeah, I don't see any difference between the mean of each box plot here. Okay, next slide. This is next slide. So I think the model generation next. Thank you.
Hi guys, so I'll be talking through how we built out the different models and the results that we generated, and ultimately how we ended up selecting the model that we felt best predicted a player's season 1 performance. So we focused primarily on regression models just because that lent itself more to the type of data that we were working on, but we also explored some unsupervised learning tools as well, and we'll delve into that a little bit later into the presentation. We did find, though, that with these other models, they were significantly more complex without, any sort of improvement in the results. So ultimately, we did end up spending more time on the regression models and devising sort of automated variable selection methodologies in order to build the best possible regression model. And as we've discussed before, the specific metric that we're looking to predict is season 1 BPM, so the box plus minus score, as Michael spoke about earlier. So for model 1, we employed a manual variable selection. And basically what we did was we included all of the per game metrics, as well as conference division information, a player's age, as well as the 2 calculated metrics that we developed, which was total scoring percentage and field goal percentage. And we found when we included all of these variables in the model, our adjusted R-squared was 0.1688, which basically translates into the fact that this model was able to predict about 17% of the variation in the data, which is not particularly high. When we were building these models, we separated our data set into a train and test set. So we took about 75% of the observations from the data set, used that to build this model, and then trained it on the remaining 25% to see how well it performed on new data. And that's where this test mean squared error metric comes from. And we got 18.00895. And so we basically looked at this test score metric, the test MSE, across all the different models, as well as the adjusted R-squared, to help us make a decision on which model had the greatest predictive capacity. So these are the fit diagnostics for this first model 1. You can see that the residuals are kind of sort of normally distributed, but there is some kind of clustering. So we're not really violating our homoscedasticity assumption, but it's not, kind of an ideal distribution that we'd like to see. And so while the results were promising, we do feel that exploring additional automatic variable selection methods might yield a stronger performance. So before we get into that, though, we tried out building a second model where instead of including all of the variables that we did, as we did with the first one, we only selected those models that appeared to be statistically significant at the 0.05% level, 0.05 level. And this model mostly just included age, division, and a handful of the per game metrics. And we found that it actually performed much more poorly than the first model did. It only accounted for about 13% of the variation in the data, and the test MSE was slightly higher, which isn't great because we want to minimize that metric as much as possible. So kind of just out the door, Model 2 doesn't look very promising. And the fit diagnostics are more or less the same as it was for Model 1 because we're using, literally all the same variables. And as I mentioned before, it did perform pretty poorly. So moving on to Model 3. So this is the first of our automatically selected models. We used forward selection for this, which is an algorithm in which we start with an empty set of variables and basically add one variable at a time until we can minimize the AIC score, which is the Akaike Information Criterion. This is a measure of model fit and complexity. So it balances how well the model is able to predict the BPM score while remaining relatively parsimonious. So with this model, we were able to generate an AIC score of 2044.34. An adjusted R-score that's fortunately a little bit higher than we were seeing. About 20% of the variation in the data is explained by this model. And a test MSE, which is a little bit higher than what we saw with the previous models, of 18.71259. And the variables that this model selected were pretty similar to what we had in the previous models. It was a lot of the per game metrics, as well as which conference a player was in, which division they were playing in, their age. These metrics kind of appear in all of the models. So they do seem to have a lot of predictive capacity. And so again, the fit diagnostics here, you see that the spread of the residuals is a little bit more evenly distributed, which is good for us because it means all of our assumptions are being held, the OLS assumptions. And so far, it gave us the strongest R-squared, but we're going to continue trying looking at other methodologies